In order to examine the motion of a falling object, I dropped a crumpled piece of paper from above my head. The origin is the center of the ball, and the ball travels in the negative y direction. The point of mass is the center of the ball. The mass of the paper is 0.0025 kilograms. The initial velocity and position are both 0. The video is 21 frames long and has a frame rate of 29.93. The principle being observed is Newton's second law with a non-zero net force. The equation for this law is Vf equals Vi plus F net over m times delta t. In the case of a falling object, the F net is equal to its weight force plus the drag force. The weight force can be modeled by negative mgj, and the drag force can be modeled by negative b v squared. In weight force, negative m is just the mass of the object, and g is 9.8, is the gravitational constant for Earth. J is the position vector. In drag force, negative b is a constant based on the object shape and its mass. V squared is just the object's velocity squared. The experiment was carried out, and using tracker, we were able to obtain data on the object's position. As you can see in the graph, we have a non-linear position versus time graph. This means that the piece of paper was accelerating as it traveled towards the ground. We can now create a computer model to compare our experimental data to. First, we'll compare it to a model with no drag force. Under the initial conditions, the mass is set to that of the crumpled paper, and the initial position and velocities are changed to 0. The g value is set to 9.8, or the gravitational constant. In the calculation loop, the t value is the total length of the video. The weight force is inserted, and the F net is set equal to W, since we are not considering the drag force. Newton's second law is then inserted to predict the future values. The data from Python can then be compared to the experimental data. For the first 0.3 seconds, the prediction is accurate. However, after this, the model overpredicts the position of the paper. This can be corrected by adding drag into the equation. Drag force is now added to the new Python code. The b value was calculated by matching the final positions of the experimental and the model data. For the crumpled paper in the experiment, the b value is 0.00087. Under the calculation loop, the drag force is added. The magnitude of the drag force is equal to negative b times the ball's velocity squared. The F net is now the weight force plus the drag force. Now when we compare the model and experimental data, the model is a lot more accurate. Between t equals 0.15 and t equals 0.5, the model slightly underpredicts the position of the paper. However, the error is small and probably contributed to not having the exact b value for the paper's mass and shape. The idea of terminal velocity can be explored by looking at the experimental data compared to the model without drag. If not for drag, the paper would accelerate all the way until it hits the ground, as shown by the curved red line. However, that's not the case, and the paper's velocity appears to level out at about the 0.45 second mark. The slope of the line becomes constant, and this means that the paper has stopped accelerating, or reached its terminal velocity. The drag force is what's responsible for slowing down the paper.